Hello, so today we are exploring topic 5, Turing machines and recursively enumerable languages. So um, that's a very long title. So this is the chapter 3 in the Stipser book, and it comes after the chapter on finite automata and on push-down automata. Okay, so the Stipser book introduces Turing machines in the simplest way, basically in the way it was defined and discovered, if we can say, in 1936 by Alan Turing, and in the way it was formalized for this whole area of investigation. Now, the thing is that we've really been on a continuum, if you noticed, since the beginning of this course, from going from finite automata, right? NFA, DFA, to push down automatas, right? And deterministic or not, and to now Turing machines. So it would be nice to define Turing machines as part of this continuum, right? And this is not exactly what is done in the book, because the book is taking the approach of defining it the most simple way and basic way, which actually makes sense, right? And I'll see what. But still, I would like to try to see how a Turing machine fits into this continuum and this kind of generalization where we add more and more power to our machines to describe a larger and larger class of languages. So a finite automata that describe that recognize the regular languages, right? If we try to schematically represent them, we could draw a diagram like that, right? Just to be very schematic. It's really just states and transitions, transition function from state to state. PDA would be basically the same thing, right? You have the states and the transitions, but you add to that the possibility of stacking information. So you add a stack with a push and pop capability, right? So you have now, in addition to the transition function, the transition function include pushing and popping into and from the stack, right? So you have this extra memory, if you want, on which you can read and write with only an access from the top. And this adds obviously some power to the automaton, right? So you now have the capability to recognize a larger class of languages, which we have looked into, called the context-free languages, right? So now Turing machine. How can we go from that to define a Turing machine? Well, there are two ways. First, we could see it as exactly like a push-down automaton, but instead of one stack, we now have two stacks, right? So here I wrote two stacks just to describe that the state of the stack is changing, but there is really truly one stack associated with the PDA, right? And now we have two stacks, and the Turing machine is actually equivalent to a PDA with two stacks, right? It's or you could say with a finite automaton with two stacks, right? So if you have one stack in addition to the what the PDA has, you get the power of a Turing machine. Now it's obviously very counterintuitive. You can imagine that you can do more things, like you can what you're going to pop out of one, you can push down into the other, and vice versa. But it's really not a convenient way of thinking about Turing machine at all, right? It's a good way of thinking of the continuum and how you increase power, right? And to relate Turing machine to PDA. But that's not very intuitive. Something that's maybe more intuitive is to think of it as instead of a PDA that would be limited by limited access to only popping and pushing from the top. You now have the capability to go up and down the stack to read any location you want and to write to any location you want. So it's not a stack anymore, truly, right? So you can now go anywhere you want on the stack. So it's really not a stack; it's really a tape, right? And we usually actually represent it, rather than representing it vertically, we usually represent the tape horizontally. And really the vertical and horizontal doesn't matter, but it really gives you an idea of the access, right? If you represent vertically, you think of a stack as something where you when you use gravity, basically, right? There's really the notion of gravity when you put like little pebbles in a big cylinder, one after the other. You're gonna be able to only reach the one on the top. You cannot go to the one on the bottom, right? If you on the contrary, you have like a ruler or some kind of container that is horizontal, and you put all the pebbles horizontally, the gravity will not prevent you from reaching any of them. You can always reach all of them because the gravity, you just put them next to each other. So really the horizontal vertical thing really only has to do with gravity, because even things like computer science are intuitively somehow anchored and rooted into nature, right, and the physical world. Always something very important to remember. So anyway, so we can define with these two approaches. Now, none of these two can beat the conventional approach, which is you have really a head reading over a tape, right? And you're a certain location on the tape, and you're going to read a certain symbol, and you can write over that symbol in the tape, right? So the actual more classical definition of what we call a configuration of the machine would be the one as described in page 168 in the book. You're going to have this Q7 01111 is going to basically mean I am at this location in the tape. So that's the tape. I'm at this location, and I'm at state Q7, and I'm actually reading over, to be more precise, the location I'm at is the one right after the state represented, right? So this configuration means the same thing as, here is the tape, and I'm here at location at state Q7. So this is my location, state Q7. Okay, so that's very simple, and then you're gonna have a transition function, just like you had for PDA and finite automata, that's going to tell you, well, what do you do when you are at such state, at such location in the on the tape? I mean, and you read such symbol on the tape. What do you do? What do you replace this symbol? What do you write at this location on the tape? And where do you move, left or right? Okay, so here is, let's look at the actual formal definition in the book. Now we've seen the more intuitive definition and also how it fits into the larger picture of automata in general. Let's look at the formal definition and try to remind ourselves of the definitions of the finite automata, NFA, DFA, and PDA. It really doesn't look that much different, right? If you look, it's a 7 tuple, so there is one extra, which is a Q reject, right? It's not much. It's just, we're just specifying what are the states that are reject states, right? So now we know we have some state that are reject state, but you could say, well, push down automata, any state that is not an accept state would be somehow a reject state. Well, there's a little difference that here, if you reach it, you know you reject. So okay, that's a little feature we didn't have before, the capacity to reject directly. That's not much. The rest looks very different, and if you look at the definition here, it looks very different. Q, the set of states, sigma, the input alphabet. We have gamma, which was the stack before, but now it's a tape alphabet. But a tape alphabet doesn't tell us anything about, you know, the computer power, right? It was a stack alphabet, a tape alphabet. It's still just an alphabet, right? It doesn't tell you about how it is manipulated. This is the important part, of course, because it tells you how it is manipulated. You take a state, you take an alphabet from the tape, and you get a state and an alphabet from the tape, and a direction left or right. If you look at that, actually it's pretty interesting because it really is very similar to PDA, and you could look at it and think, what's the big deal? How does it change so much what we had before? Because it's really not that different. Actually, you could even argue that a PDA and an NFA at least have the capability to go to multiple states because of their non-determinism. This one is deterministic. It doesn't even have a power set here. So it doesn't look, and if you look at PDAs actually had sigma cross Q cross gamma. So you even had more information in some sense in the PDA. So you could say, well, what's the big deal, right? Well, the big deal is really LR. And when you look at it, it's like, well, okay, you just give the capacity to go left or right. And before that, you just had the capacity to pop out and push down. Well, that's the whole thing. And that's what is so interesting about Turing machines, that you add just this little capability of going left or right, and somehow, well, it changes everything, right? It's really, as we just said, it's really adding this power to go through the stack, inside the stack, way down below. And so that's just something to notice, that this little change actually changes everything in terms of computing power. Everything to the point that, yes, you can add non-determinism, you can do multi-tape Turing machine, you can do all kind of improvement of that. It will not change the computing power of a Turing machine. It will not add any power. It will make things more simple, right? Just like some languages, programming language makes things more simple, are more readable, more concise. Yes, but it will not add any computing power like Turing machine adds computing power to a PDA and PDA adds to an NFA. No. And this is the notion, the very important notion of robustness that is given in the book at some point, is that the idea that a model is doesn't change its expressivity and computing power, will not see its computing power changed even by adding some different variants or changes to its characteristics. And in this sense, Turing machines are very robust because you can add all kind of features. It will not change their computing power. You could contrast that with the PDA, which is almost the opposite, right? We saw that a PDA, if you add determinism, you have something very different from a non-deterministic PDA. So in some sense, a PDA is not very robust in this sense, okay? So a language is said to be Turing recognizable or recursively enumerable if it can be recognized by a Turing machine, right? So recursively enumerable is the same thing as Turing recognizable. Personally, I think I've seen more often recursively enumerable languages used than Turing recognizable. And then we also call the set of languages that are that can be decided upon Turing decidable, right? So the set of languages that can be decided, that's very important, right? Turing machines are defined in such a way that they can loop forever. You can design a machine, it's actually very easy to do, that will never reach an accept or reject state. And so for obvious reasons, we are very interested in a class of languages that are decidable. That means that can be recognized by a Turing machine that will not loop forever. Okay, that will either reach at some point an accept or reject state. So that's the notion of decidability, which we'll cover much more in depth later on. Okay, so the book goes on to give some formal description of a Turing machine, right? So I suggest you look at it at least in detail once or twice, page 171 and 172. You have a formal description. That means the full definition of the Turing machine, that Turing machine, right? It's one Turing machine, it's not Turing machines in general, right? We just saw the formal description of Turing machines in general, right? It's they have to be defined in those terms. Now you can define. You have one example of such definition at the bottom of page 171 and the top of page 172. It is important to look at it once and really try to understand it, because that's what it is, formally, fully defined, completely from A to Z. You will not look at it again, because we never do that, right? We never define the Turing machine completely. It's just too tedious, too much details, and that's actually not really needed, right? It's just at some point, I mean, it's just like defining the machine that recognizes 0 star 1 star is easy with a finite automaton, so it's fun to play with it and to really actually define it. But with a Turing machine, it's not as easy. It's very fast. It's very tedious, and in the end, what we're really interested in is more the language and the high definition of the machine, what it does in English words, or in kind of a pseudo code, pseudo algorithm, and so that's more what we'll focus on. But this will truly make sense only if you have been through actually analyzing the formal Turing machine at least once or twice, the complete description of the Turing machine. So there are different variants of Turing machines, and that's described in the book. Multi-tape Turing machine, non-deterministic Turing machines, and they show the enumerators. They show that they're all equivalent to Turing machines. They don't have any computation power, as we just said. So the non-deterministic Turing machine, unsurprisingly, has the famous power set that we've seen before, right? So it really is a very simple addition to the Turing machine. It is a very, very interesting and I think powerful theorem that every non-deterministic Turing machine has an equivalent deterministic Turing machine. And it's not that hard to see, and I suggest you look quickly at the proof. The basic idea is that you can describe non-deterministic Turing machine as a tree of deterministic Turing machines, right? So the machine is going to start at some point, and then maybe it's going to be deterministic for a while, but then at some point it's going to branch into different options, and it's going to reach different states. The idea is to say that you can actually cover all these states via an equivalent Turing machines that will go through all of these. The important part, and if the non-deterministic is stops at some point, your new machine will stop, and if it doesn't stop, it will not stop, right? The important point of the proof is that instead of having the machine go, the new machine you design that is supposed to simulate the non-deterministic one, the deterministic machine you're gonna build is gonna be built upon whatever this one does, right? But the key idea is do not go a depth first search into the graph, into the tree. If you do that, you could end up into one of these that loop forever, right? So let's say that this is a presentation of a path that loops forever. You do not want to do depth first search, because if you do that, your new Turing machine is not equivalent to the first one because it didn't cover all of these states, right? And it's going to miss all the other ones because it loops forever, and it fell into a kind of vortex, if you want. So the Turing machine you design that simulates this one has to somehow go through these states by doing a breadth first search, right? So the breadth first search is width. You go through the width, right? You traverse by using the width. So you do this, and you cover all the states that are the same level on a tree of the tree, the same level of the tree, same hierarchy on the tree at once. I mean at once, and then the next level. You go level by level, right? By doing that, you are ensured of covering all the states of the non-deterministic Turing machine. Okay, that's just a very interesting proof, and that's just a very, very interesting result. Of course, that as you can imagine, that doesn't mean that a non-deterministic Turing machine is going to be as efficient if we start thinking in terms of complexity, time complexity, and space complexity. You can solve things in a much shorter time and much less complexity with a non-deterministic Turing machine as a deterministic Turing machine. But that doesn't affect the computing power. What you can do with one, you can do with the other. It's a very, very important result. When you think, even when you think about things like quantum computing and things like that, it mostly affects really the efficiency and complexity. Okay, not the computing power. So that's the important points from this chapter, and that's mostly what I wanted to cover. The definition of you have the idea of the equivalence with other models. The book on page 182 mentions an important aspect of that. Is that implication of that is that obviously a Turing complete language, a programming language, is equivalent to another Turing complete programming language, right? What you can do with Lisp, you can do with C, or with Java, or with Prolog, and vice versa. So that's one of the very, very important results of this equivalence of any Turing complete language and machine. So the definition of the algorithm is also an important point. The Church-Turing thesis tells us that basically a Turing machine algorithm is the right formal definition, but for what we've intuitively understood as an algorithm without formal definition so far. So that's the best definition of an algorithm, is a Turing machine algorithm. And so basically anything computable should be computable by a Turing machine. And so then it raises some questions about what is computable, what is not, and there is this whole idea about finding the root of a polynomial, and when we look at the polynomial on page 184, we see that it makes a big difference if you have a bounded universe or not, right? Do you want to find a root for any polynomial, or for a polynomial of degree n and below, right? If you bound your universe, you can find a Turing machine that computes that. If you don't, you can't, right? So it's the notion of bounding is very important, and that's kind of an introduction to the next topic on linearly bounded automaton, right?